What we're going to do today is just going over the all the important equations that you should have on your formula sheet, and also kind of like refreshers about what you have learned. Okay, so starting with chapter 36, which is about diffraction. So there are a couple of different type of diffraction. So you need to know under which condition that under which condition under which setting that you want to use which equations. Okay, so for example, if we're going to do diffraction, let's say diffraction by a single slit. So if we are doing diffraction, if the diffraction is caused by a single slit, then we know that because the mathematical difficulties, so we are only able to derive equations for the dark fringe, which is different from the interference pattern produced by a double slit. So that's a diffraction by a single slit. So you have a single slit, light goes through the single slit, and it's going to produce a diffraction pattern. And we're able to deduce where the dark fringe will occur. So the dark fringe will occur according to this equation: a sine theta that is equal to m lambda. And a, of course, your A here is the slip width, and sine theta, and your theta is is the location, is the angular positions of the dark fringe. And your m starts from 1 to 3. You don't have a 0 because we're looking for dark fringes, so it's 1, 2, 3, and etc. Okay. And regarding the intensity of the line, or intensity of the line, the bright fringes, then the equation is this: I of theta, which is the function of the angle, and that is equal to the intensity at central maxima, which you use the I sub m, and then times sine theta, sine alpha, and over alpha, and then you square the whole thing. Okay, and alpha here can be calculated using pi a, and then over lambda, and then times sine theta. Okay, the important thing about this equation is that you want to remember that alpha here in this context, that will be in radians. So make sure that you don't, this will be in radians, but when you plug into this equation, when you plug into this, this sine alpha, it really depends on, the mode on your calculator, whether it is in radians or in degrees. So when you punch into the calculator, you do have to kind of think about what mode on your calculator that you set for to calculate sine or cosine. Okay. So the important thing is that when you use this equation, to calculate alpha, that will be in radians. And then when you plug into this sine alpha, then either you can convert it to degrees, or you keep it in radian mode if that's what you set on your calculator. Okay, so this describes intensity as a function of the angle of the bright fringes produced by the single slit. Okay, and now we also mentioned diffraction by double slit. So for diffraction produced by double slit, so I'm just going to shorthand this because it's not easy to write this with the mouse. Okay, so diffraction by a double slit. For diffraction by a double slit, the intensity of the bright fringes takes up this form, which is intensity as a function of angle, that's equal to the intensity at central maximum, and then times cosine square, cosine beta square, and then times defect from the single slit, sine alpha over alpha, and then you square it. So if you compare these two equations, you can definitely see that the diffraction by a double slit, involves this term which comes from the single slit, and so this one is for double slit. And what is your beta? Your beta here is equal to the pi, and then your d, and then your lambda, the wavelength of light that sent through the slit, and then times sine theta. Okay, so d here is the slit spacing because we're talking about double slit. So that's a slit space. D is your slit spacing, and your A is the slit width. Okay. All right. So so again, this beta will be in radians. Okay. So if that's in radians, so when you punch in, when you key into this to calculate cosine beta, you want to make sure that it's the same thing whether you calculate setting the degree mode or the radian mode. Okay, and then there's also diffraction that say light goes through a circular aperture. In that case, then we're able to find the first, the location where the first minima occur. You have no sound. What do you mean? You cannot hear? Yeah. So Martin, you might want to check your setting. I don't know what's going on. All right. Diffraction by a circular aperture. So if you have diffraction, if you have light go through a circular aperture, then the equation to find the first minimum produced by the circular aperture is this. So sine theta is equal to 1.22 and then lambda over d. Okay, so again, lambda here is the wavelength, but d here is not. D here stands for the diameter of the circular aperture. So it is the diameter of the circular aperture. It is not the slit spacing because we're talking about the circular aperture. So let's say you have a lens, and then the diameter here is your d. Okay, so this is the equation, to produce the first minimum. Okay. Again, so that's just for the first minimum. And we also mentioned, we also discussed in class that when you want to use when light goes through the circular aperture, it's going to produce diffraction pattern. So if you have if you have more than one object, that each is going to produce the diffraction pattern. Sometimes, depending on how good is your circular aperture, you may not be able to resolve it. So in that case, certain condition has to be satisfied so that you can actually resolve the diffraction pattern produced by, let's say, by two distant objects. So in that case, this the condition is called the Rowley criterion for resolvability. Okay, so what is that resolvability? And what he found was that the angular separations of the circular diffraction pattern has to satisfy the following condition. Rayleigh's criterion for resolvability. And that is the angular separation between any two distant objects theta has to be equal or greater than the theta r, and theta r is the theta sub r, which is the Rayleigh's angle, and that is the inverse sine and 1.22 wavelength of the light over the diameter of the lens. Okay, So it really depends on the how good your lens is. Then you can you can use this equation to determine whether your lens is good enough to resolve the two distance object, because each object is going to produce a diffraction pattern. Okay, and this equation, because usually you use this to determine the very distant object. So in other words, the angle will be very small, and so usually this can be approximated by this 1.22, and then lambda over the diameter of the circular aperture. Okay, now inverse sine of this is equal to what's inside the argument is valid only when the angle is very small. Okay, so if we apply this to astronomical objects, usually they are very far away, so that's why the angular separation between the objects is very small. So this is valid. So this is diffraction pattern produced by the circular aperture. We also mentioned that when you send X-ray through the through crystalline like crystalline that sort of objects, you can produce diffraction pattern as well, and we use that to study how the ions are organized in to produce to produce the compound. So this is what we call the X-ray diffraction. So X-ray diffraction. So in other words, when you send light that is in the range of X-ray, which is a very short wavelength, and then let it go through let's say NaCl, the table salt, is going to produce a diffraction pattern, and then Bragg found that by Bragg's law, he found that the diffraction pattern produced by this obeys the following equation, which we call that Bragg's law. What he found is that if light, go through this, you have 2D sine theta that is equal to n lambda. That will produce a bright fringes. That predicts where the bright fringes will occur. And then D here is the spacing, planar spacing. And sine theta and theta, we're going to draw that. Okay, your m here is the order number. So your m here is 1, 2, 3, and etc. The integer, and lambda, of course, is the wavelength. Okay, this is for bright fringe, and that's different from. So this is like we use the the lattice structure of the compound, and then light goes through that the lattice, and it's going to light is going to be scattered and produce a diffraction pattern. It's going to produce the bright fringes, and this equation describes where the bright fringes will occur. To the sine theta is equal to n lambda. Now this is the diagram that say you have like this plane and that plane. You have like all these ions that is orderly arranged like this, and this is what we call the spacing of the diffraction plane. And then you have light, so this is our normal. So when you have light go through this, it's going to be refracted. Okay, I'm drawing this because I want to let you know that this is the angle theta we're referring to, not this angle. Okay, so this is different from when we talk about the angle of incidence and angle of refraction. The angle of incidence here is not in reference to to the normal. The angle of incidence theta is in reference to to the angle between the incident ray and the reflecting plane. Okay, so that's the difference between. So this is the angle we use. All right, so these are the important equations from and also concepts from chapter 36. Any questions so far? if we don't have any question, let's move on to chapter 38, which deal with quantum, photons, electrons, those subatomic particles. Now, when we talk about quantum mechanics, the one thing that we know is that light can no longer be considered as wave. It also has it also acts as a particle. So, in that particle we call a photon. And with that, we have an equation that we can use to calculate photon's energy. So, for photon, if you want to calculate the energy of a photon, then E is equal to hf. So h here is a Planck constant, and f here is the frequency. So it depends on the frequency of light. You can calculate the energy contained by the photon, which is h times f. And we also mentioned that the momentum of photon can be calculated using this equation. So your P here, that's momentum, which is equal to E over C. E, of course, is the energy of a photon, which you use this equation, hf. And then C is the speed of light. This is one equation you can use. The other equation that you can use is this, h over lambda. Okay, so in other words, once you know the wavelength of light, you can calculate the momentum. You can also calculate the energy of a photon. Because if you remember, what is F times what is that equation? That relates the frequency and also the wavelength, the frequency and the speed of light. So F lambda is equal to the speed of light. So in this case, you know that once you know the wavelength, you can calculate the frequency. Or if you know the frequency, you can use this equation to calculate the wavelength. And in both cases, you can actually you can further calculate the energy and photon. Okay. So in other words, as long as you know either frequency or wavelength, you'll be able to figure out what the energy of the photon is, what the momentum of the photon. Yeah, that's good. Thanks, Martin. All right. So, So that's the energy of momentum. I'm sorry, that's the energy of the photon and momentum of the photon. Now, the Planck constant has two different units. So again, when you do calculation, you want to make sure that you are using the SI units so that you don't get confused. You do not want to mix the SI the quantity with the SI unit with the quantity that is in non-SI unit, because then you are going to get wrong answers. You want to make sure that your units are consistent. Okay, and the best way would be that just convert everything to SI units so that you don't get confused. You don't, you'll get you'll make sure that you're on the right track. Okay, so again, the Planck constant will be given. So you want to make sure you're using the SI unit one. So in that case, so I'm not going to write it out because it's just, yeah. But so in that case, a lot of times, your energy will be expressed in terms of EV. You want to make sure you know how to convert that. 1 EV is equal to 1.6 times 10 to the negative 19 joules. Okay? So I would strongly recommend you that just change everything to joules so that you don't get mixed mixed units. All right. Now, in chapter 38, there are a couple important experiments that we talk about. The first one is the photoelectric effect. Okay, so the photoelectric effect describes the interaction between the between the photons and also the electrons. So this is what we call the photoelectric effect, and based on conservation of energy, we know that the energy of a photon, okay, is equal to the maximum kinetic energy of the electron, if there's any left over, plus the work function, which is the binding energy of the electron to the nucleus. Okay, so this is what we call the work function. And again, most of the time this will be given in EV. So you do want to convert it to to the SI unit so that you don't get confused. So this is called work function. Okay, so for the electric effect will occur only when the energy of the photon is greater or equal to the work function. If it's equal to work function, which means that the photon has just enough energy to keep the electron out of the nucleus, the atoms. Now, if there's more than just the work, if the photon has more energy, more than just the work function, then the rest will be picked up by the electron because energy is conserved. Okay, so if the energy of the photon is greater or equal to the work function, then photoelectric effect will occur. Will happens or occur. Just say occur. Now, if the energy of a photon is less than work function, which means that the photon is not energetic enough, then photoelectric effect will not occur. Okay. Now, in addition to the photoelectric effect, we also introduce the Compton's experiments. Compton experiment also described how the photon interact with the atoms. Okay, so for Compton's experiment, what we found is that again, based on conservation of the energy, the energy of the incident photon has to be equal to the energy of outgoing photon, and then plus the energy of the kinetic energy of the electron if there's any left over. Okay, so the situations like this, you have a target right here, and you have the photon that's incident on the target, and let's say the energy of photon is E, which is HF, and then with the wavelength, let's say lambda, and we mentioned on previous slides that once you know the energy, you can actually calculate the lambda. So either way, if you know one quantity, you know the other quantity. And so the outgoing photon, we use E prime to indicate that's the energy of outgoing photon. And then the wavelength will change to lambda prime. And if there's any leftover energy, then it'll be picked up by the electron. Okay, that's electron, let's say with kinetic energy K. So this is based on conservation energy. HF is equal to HF prime plus K. And then what's going to happen is that there is a wavelength shift because lambda becomes will produce another photon that has a wavelength over lambda prime. And the shift we call the Compton shift. So Compton shift is called delta lambda, and it can be calculated in the following manner. If you know lambda prime, then by using a longer wavelength minus the incident, by using the wavelength of outgoing photon minus the wavelength of incident photon, that gives you the Compton shift. Now the other equation you can use is that it can also be calculated using this equation, the Planck constant over the mass of the electron in this case, and then times the speed of light, and then times 1 minus cosine, and then the angle. So it really depends on where the detector is located in reference to the horizontal line, and that's your angle phi. So once you know the angle, plug into that equation, you'll be able to figure out what the Compton shift is. Okay. And the other thing, so Doha lambda can be calculated either using this equation or use that equation. So you can see that once you know the angle phi, you can use this equation and then calculate, the Compton shift. And if you know one of the wavelength, then you can use this equation to calculate the other wavelength. Okay. And so this one, the one in front of the parentheses, we call the Compton wavelength. Okay. All right. So that's that. And we also mentioned that whenever you have a subatomic particle like electron, protons, photons, all these are called matter waves. Okay. Now with matter waves, we know that they satisfy Schrödinger's equation, and there's a wavelength associated with these particles. So in other words, now this particle behave like a wave. So like electron or proton. So in a way, the wave is what we call, and it also has the wavelength, and that wavelength we call it the Broglie wavelength. And how do we calculate the Broglie wavelength associated with the electrons and protons? The wavelength can be calculated using this equation. Lambda is equal to h over p. Or if you prefer, you can say that P is equal to H over lambda. So in other words, when you're dealing with electron, proton, this is the equation to calculate the momentum. Okay, you cannot use E over C because E over C that's just for photon only. Now for electron, proton, you use H over lambda. And lambda is equal to H over P. That's that's what we call the de Broglie wavelength. Okay. Now, we mentioned about matter waves. In other words, all these subatomic particles now can behave like a wave, and it has to be governed by the Schrödinger's equation. And so Schrödinger's equation describes how these electrons, these this subatomic particles behave. And so Schrödinger's equation, let's say Schrödinger's equation. In a one-dimensional case, and in a time independent, in other words, we already remove the time, is this. So let's say you have a particle and moving a one-dimensional direction and oscillate and the time information is removed. Then how the electron behave, and it can be described by the Schrödinger's equation. And the equation is this. It is the second order differential equation. So the C here is your wave function, and then that's a solution to the Schrödinger's equation. Okay, so that just gives you some idea about what this equation looks like. So so you deal with the mass of the particle. You have the h squared, and then within this bracket you have the energy difference, the energy of the particle minus the potential, potential energy that it has, and then times the wave function here. Now again, we mentioned that the solution of this is the wave function, which is which is not physical. In other words, we cannot really measure it. The only quantity that we can measure is is the probability density, which is the wave function square. Okay, and that is something that is physical that we can actually measure it. So the distinction between C and C square, absolute value square, is that this is wave function, which is a solution of the Schrödinger equation, and it is because it involves the imaginary number, so it is it's not physical. Yeah, okay, and the C square is called probability density, which is which is the one that we use to find where the particle would be. Okay, so that's probability density. Okay, and we also mentioned something about the uncertainty. So the uncertainty principle was proposed by Heisenberg. So we call the Heisenberg's uncertain principle. So what is Heisenberg's uncertainty principle is about? It means that when you have a particle, you cannot have the exact measurement of both the position and the momentum simultaneously. If you know one quantity precisely, you lose the information of the other. Okay, so Heisenberg's uncertainty principle in mathematical form says that the uncertainty in position times the uncertainty in the linear momentum in the same direction has to be greater or equal to Planck constant over 2 pi. So you can extend this to like 2-dimensional or 3-dimensional. In that case, you have delta y times delta p sub y, delta z times delta p sub z. So it only governs the position, the uncertainty in position, and also the uncertainty of the linear momentum in the same dimension. Okay. So in other words, you do not have the cross product like delta x times the delta p sub y, which is there's no such relationship. Okay. And regarding energy and time, interestingly, it also follows uncertainty principles. It also follows the Heisenberg's uncertainty principle. So you have your delta E, and then you have your delta T, and that must be greater or equal to h over 2 pi. Okay, so that those are the equation that is described by the Heisenberg's uncertainty principle. And the last concept that we discussed in chapter 38 is the tunneling effect. So what is tunneling effect? Tunneling effect basically is quantum effect. It just means that there's non-zero probability of the particle that can appear on the other side of the barrier. Okay, so schematically, this is something like this. You have the positions, and you have the let's say this is the barrier, and let's say you have the barrier, and this is the energy axis. You have this, something like this. So you have a particle that's incident from the left, and then classical, and then because this is on the energy diagram, so you have the particle that with the energy that's less than E, so it will be you will not be able to classically you will not be able to appear on the other side of the barrier, but quantum mechanically there's a non-zero probability for that to occur. So in other words, this is 0, this is L, and this is your X position, and this is your probability density. What we found here is that on the left-hand side, the particle basically act like a free particle So when you have a free particle, it actually oscillate like this. And then on the right side, it will go like this. So the important thing here is that it is non-zero, because classically we would predict that it should be zero. The particle, that because it does not have enough energy, it would not be able to appear on the other side. But quantum mechanically, that can happen. Okay. Any questions so far regarding chapter 38? I know it's kind of a lot of stuff, but I just want to like go over the important concept we that we discussed in class. Of course, not all of them will be on the exam, but so yeah, just want to give you a more comprehensive review. Okay, now let's move on to chapter 39, the last chapter for the working problems. Okay, now chapter 39 deal with there are two important concepts in chapter 39, which is when you have an electron that's trapped in the infinite potential world, and also applying to a realistic case when you have an electron that's trapped in a finite potential world, like a hydrogen atom. Okay, so there are a couple of things, and also chapter 39 introduced a couple concepts. One is the confinement principle. So what is confinement principle? Confinement principle, I mean, you can go over the notes, and then we'll give you a more description. But the important thing about confinement principle is that when you have an electron, or when you have, let's say, take for example, when you have an electron that's confined within is confined, then it can only exist in a certain state, and then and then it becomes quantized. So in other words, the important thing about confinement principle is that quantization of the energy states of the electron is due to confinement, because it's confined, so it can only exist in certain states. So quantization is due to confinement. Okay, so now let's say you have an electron that is trapped in an infinite potential world. Okay, so let me just draw a diagram. So you have this, let's say this is positioned, you have 0 to L, and then this is potential. It goes to infinity, and you have an electron that's trapped inside this potential world. And then so we're interested to know what kind of energy that electron can have, and also what is the probability of finding electron at what location. Okay, what we found here is that the energy of electron is this, which is quantized. E sub n is equal to h squared, and then over 8 times m times L squared. L is the well width. So the whole thing here times n squared. And your m here start from 1, 2, 3, and etc. So in other words, you do not have zero energy. When the electrons combine, there's no zero energy. There's always a minimal energy presence, because just by looking at this equation. Okay, and the wave function is this, which also involves the quantum number. So the principal quantum number. So the wave function is a times sine theta, sine, and then within the argument you have n pi over L, and then some x. Okay, and also what we know here is that the boundary condition is that the wave function at 0 and the wave function at L has no value. So in other words, the wave function when x is equal to 0 is 0, and when x is equal to L is also 0. This is when you're dealing with an infinite potential well. Okay, and you have the energy of the electron that behaves like this, and the wave function is this. So if we draw the energy diagrams of the electron, what we have here is that, let's say this is energy. So you start from the ground state. With this ground state, we call that E1. So when n equal to 1, this is called ground state. When n equal to 2, we call that first excited state. When n equal to 3, we call that the second excited state. So the nomenclature, you want to make sure that you follow that. This is ground, this is first excited state, and this is second excited state. And we also mentioned that electrons, if we want to change the, if the electron is making transition between states, it can be achieved either by absorbing or emitting a photon. Okay, and the energy of the photon must be equal to the energy difference of the states. So in other words, the change in energy delta E is equal to, let's say, it's always the energy of at a higher level minus the energy at a lower level. And that energy difference must be equal to the energy of photon. Energy of photon, of course, is h times f, and is equal to hc over lambda. So in this case, you can calculate what kind of wavelength of photon that must be absorbed or received must be absorbed or emitted by the electron in order for the electron to change its states. Okay, so if the arrow is going in this direction, which means that it's going to emit a photon. Now, if the direction is from the lower state to higher state, then it has to be, a photon has to be absorbed. In either case, the energy difference is just, use the previous equation. Use this equation. This equation is the energy, so just plug in, your n number here, and then you can calculate the energy difference and set it equal to the energy of a photon. Then you can calculate the wavelength of the photon. Okay. And the other thing that we are interested in knowing is that what is the probability of finding electron within certain range. So in order to calculate the probability of finding electron, let's say within x1 and x2, this is how you calculate. So probability of finding electron between, let's say, x1 and x2, then of course would be the probability density, and then you integrate that. So because we're dealing with the the one-dimensional electron, so we know that would be, we already know the wave function, so we just square it. So we have this. I'm sorry. This is what I want to write. You have your x1 to x2, and then the wave function square, that will give you the a square, which is the amplitude, and then times sine square, and then you have your m pi over L, and then times x, and then you have your dx. Okay, so that's your probability of finding electron that is trapping your infinite potential well within from the range x1 and x2. Okay, so we discussed how to calculate the probability And when we did problems like that in class, and also in the online lecture as well. So that's something here. And so the important thing I want to mention qualitatively is that if any, let's say this is the infinite potential world, and this is the from 0 to L. Okay, when n equal to 1, without calculating the probability, you know that it only has one peak. And we also know that the wave function has 0 value at the boundaries, and you only have one peak. It can only occur like this. Okay, with the largest probability of finding electron in the middle of the well. Now, if the electron is in the first excited state when n equals 2, if that's in the first excited state, n equals to 2, which means that it has two peaks. If it has two peaks, it means that you will have one peak that is occurred at a quarter L, and another peak that's occurred at three quarters. Okay, and then if n equals to 3, which is the second excited state, you then expect that you should have 3 peaks, and etc. So you have 1, you have 2, and they are equally divided, right? So this is like, without going through the calculation, you were able to actually, just based on the quantum number, you'll be able to kind of deduce what will be the probability of find where the peak what is the location for the peak to occur. Okay. And so this is when you have an electron that's trapped in an infinite potential world. Now, if you have an electron that's trapped in a finite potential world, if that's trapped in a finite potential world, then the salient feature still remains the same. You have 0, 0. That's say when n equal to 1. When the electron is trapped in a finite potential world, the ground state will behave like this. The wave function will be like this, or the probability of finding electron. So in other words, this is when you have this is when they are in the infinite potential world, you have 0 at the boundary, 0 at the boundary. But when it's trapped in a finite potential world, this is non-zero. Okay, outside the boundary is non-zero. So that's a major difference between those two, whether it's trapped in the infinite or a finite potential world. Okay, so when the electron trapped in a finite potential world, when n equals to 2, you would expect there are two peaks, but then it extends beyond the well width. Okay, so it's non-zero, on both sides. Okay, and so let's see. Now this is the pictures when we're dealing with the electron in one dimensional. We mentioned in class that you can have a realistic situation when the electron is trapped in a three-dimensional world. Then in that case, there might be states. There might be states that they have the same energy, and those states we call that degenerate states, which means that energy of the electron, different state can have the same energy. Okay, and you can go back to your notes to just look at the equations, and you will know that. We also mentioned about correspondence principle. What basically what correspondence principle is about is that when the quantum number is large, the predictions of quantum mechanics merge with those of classical physics. So in other words, when n becomes very large, you'll find out the calculations of quantum mechanics matches very well with the classical calculation based on classical physics. Okay, and the one last concept is when we apply the when we discuss a realistic situation, when you have an electron that's in the hydrogen atom, okay. So when you have an electron that's trapped in the hydrogen atom, we we discuss the energy of the electron can have. Again, because it's being confined, so it can only exist in quantized state in certain states, and those states are called quantum states. Okay, so the energy of the electron when it's trapped in the hydrogen is this: negative 13.6 over n squared, and this is in eV. So when you do calculation, when you're asked to calculate, if you just want to calculate the energy difference, you can keep the energy difference in eV. But when you want to calculate the wavelength, you want to make sure that the energy is converted to joules, because wavelength is in meters, and that's an SI unit. Okay, so when you do calculation, you want to make sure that everything is consistent unit-wise. Okay, and so this is the energy of the electron. Based on this, we can actually draw the energy level. Okay, so let's say, okay, this is E1, the ground state, or n equal to 1, and then you have your n equal to 2, you have your E2, and then you have your E3. They are not equally spaced, but they are actually getting closer and closer. Okay, and then let's say this is your E4, then you have E5, blah blah blah. And then what we found here is that if if the electron wants to change states, it can accomplish either by absorbing or emitting a photon, and the energy of the photon must be equal to the changing energy. Okay, and when the electron changes state and emit a photon or absorb a photon, if it goes through, let's say from this to this, if it starts or ends at quantum number n equal to 1, so I'm going to draw both arrows to indicate it can jump up or jump down. When you have emission lines or absorbing line that ends with 1 or start with 1, this line is what we call a Lyman series. We have another series that ends at quantum number 2, which is the first excited states. Of course, you have another one that's but we didn't discuss. So all this, when it ends or start with n equal to 2, we call that Balmer series. Most of the time, people are more interested in Balmer series because the photon has a wavelength in this series. The photon in this series have the wavelength that's invisible lights. Okay, so how do we calculate the change in energy? How do we calculate the wavelength of a photon? Again, the change in energy is equal to the energy of the electron in higher energy states minus the energy of the electron in a lower energy state, and that energy difference must be equal to hc over lambda, or the energy of the photon. So when you do this calculation, make sure that you convert it to the SI unit before you calculate your wavelength. Okay? And just by looking at this, we know that in order for the series to produce a largest wavelength, we must have the smallest energy difference. Okay? Smallest delta E. So again, depending on which series you start with, let's say if the series is Balmer, then it can either go up or go down. You have to have n equal to 2. When you're dealing with a Lyman series, then one of the one of the energy must be equal to 1, and then you can, let's say with this, let's say with the Lyman series, this will be the smallest energy change, which will produce the largest wavelength. And so the energy difference will be E2 minus E1. Now, if you have, if you want to, if you want to have the smallest wavelength, which means that you want to have a largest energy difference, so that will be from this to this. This is when infinity. So you'll have, you'll have the e to the infinity minus e1. This is when you're dealing with the Lyman series. If you're dealing with the Balmer series, then the shortest energy difference then will be 2 and 3, and the largest energy difference will be in infinity to e2. So in other words, you have to have, in either case, you have to have e2, okay, as a base values. Okay. And that's it. That's about the we're done with the the most important equations that you should have on your formula sheet. Any questions so far? Well, what you need to know in chapter 40 is about, I'm sure that you already read the sections that I picked out for you, and then you also need to know the multiple choice questions. So as long as you know as long as you understand the concept and was able to answer the questions of that quiz, then you should be fine. Okay. So like I said, chapter 40 will be just I will just pick like 1 or 2 multiple choice questions on the final. So the working problems are mainly on chapter 36, 38, and 39. Any other questions? So again, these are just a comprehensive overview of the things that we discuss in class. You want to once you know the concept, you want to make sure you know how to successfully apply them to problems. So in that case, I strongly recommend you going over the problems that we did in class, and also going over just go also going over the quizzes that we had, and that should be fine. And also make sure that SI unit, you want to keep within the context of SI unit. You don't want to mix with numbers and stuff. Okay. Any other questions? If no, I'm going to stop the recording because I don't want it to get too long.